Hello, welcome to the part 26. Sorry about that. It was just my Chromebook. We're gonna start over with the ABC's possible terminology with the second semester. So I'm gonna keep going through it. I'm not sure how well I'm gonna make it, so hopefully I'll make it around to the X-ray. Yeah. I'm gonna the thing before I start this video. Science was sponsored by this video. I don't know if I put I don't know if I put the description on this video. Most people will know that it's science related, so I don't really have to put I don't really have to put the description around here. I really don't have to put the description. You guys know that science is actually sponsored by this video. Um, Most people would just know that it's science related. I normally do that whenever doing a lab, or I'm doing the science experiment. That could be it. So definitely, I'm gonna move this right here if you don't mind. Yeah. Harmonic motion, harmonic motion, harmonic motion. Repeat. Harmonic motion, harmonic motion. Harmonic motion is a simple harmonic motion is a special type. For this example of y equals a sin cos equals a sin. Sorry, that was my phone. Square root of a divide by I don't know. What do you think What do you think the answers are for? What do you think they are? I know it says like something about one. I think I'm not sure what it looks like. Just gonna say a divided by 11 equals 1. I think. I'm not sure. What do you think it is? All right, so I cannot tell if it's f or not, but I can tell it's f equals 1 out of 1 divided by 1, which is provided by this line. So there's a pump with the looks like a straw that you drink, but this is not exactly for that. So all right, so down here is what do you think what do you think that down answer is? What do you think that is? Because I cannot read it very well. So I cannot read it very well because I cannot read it very well. So what do you think it is? Tell me in the comments, please. I'm gonna move this if you don't mind. All right. All right. So this is the f equals 0 divided by 2a. So yeah, you see those lines going in a different direction, which is the staying as a normal size. It usually stays like a normal size, like normal lines that would be normal for a line. So yeah, that's what harmonic motion actually represents to. Like, so the third picture is actually the Vmax is actually the green arrow, and there's a P, which is a purple circle line, and there's this point undergoes simple harmonic motion, which is that dot was sitting around this looking triangle thing. Yeah. Yeah, so there's a 0 degree on that triangle, so we all know that triangle is 180 degrees. So yeah, it's for x is through those two lines, two short lines, but there's a W in the blue arrow, which is turning down. Okay, so the x, square root of x squared minus x squared. You can tell the difference between this. The x is big and the little x, so you can actually tell what it is. So yeah, just to remind you guys. All right, so the real space is actually what it's been represented to. So if you look at this line, looks like this zigzag line goes through all looking like that it looks like a bridge, but it's not. But it looks like a bridge to me. But it's like turning up to a bridge, and it also turns down to to this bucket with the hole in it. So yeah. So the phase space is actually the orbit line or orbit circle line. So the green dot is actually sorry guys, I'm tired. Been up all night. Well, not up all night. I just woke up at two. I just woke up at three. I just woke up at 2:30 in the morning. So yeah. Position is the dash black line, and the velocity is actually the gray dash line with the velocity. That's where it represents to. So sorry, I'm just so tired right now. I I don't know what I'm gonna be doing today. I'm probably gonna eat some fish. That's about it. Yeah, I'm gonna get fish for red lobster, but my mom doesn't like red lobster, so yeah. Alright, so my mom's going to church today, so she might bring me back a little something, even though I'm kind of hungry, but I can deal with it. So the procession is actually the black dash line, which is kind of like the same as the velocity mode, except this line. So yeah, like the orbit is actually a circle, or it can be like in yeah, looks like a circle, but like it turns out to be this one right there, but it's actually more different than that. What do you think it represents to? Sorry. All right, so the F S down squared A and X. So this is what I'm gonna pretend that it's like a swing club or something like that. I'm gonna pretend it's like karaoke or something like that. Yeah, I'm gonna pretend that's that. It also has that same movement of that different amounts of what it actually does is actually this is about the harmonic motion or the definition of a simple harmonic motion. Any periodic back and forth motion produced by a restoring force that is directly proportional to the displacement and in the opposite direction. But but displacement centers around an equilibrium position. So this picture represents that. So it means like B to A to C. So B looks like one of those zigzag lines. Kind of looks like an M, but it looks like more like an M to me. But yeah, this that actually says the M. So this is the F turning to the left, and this is how the movement goes by simple harmonic motion. So this is the A has been located at which the dashed lines. Why do I keep pressing the wrong button? All right, so all right, I think do you guys, if you guys have any questions about the this page, just let me know. I'll be happy to answer you. All right, so the A is that it looks like almost the same, but it's not the same as the B because the B is more like relent. So it's a little fast, but it's not too fast as the A. So it's a little bit too fast, like the A. For example, this is the M, the same. All of those are M, so this is actually 0. When the 2 adds a little bit more, but the 0 just looks like it's simply normal. So it could be around it. What do you think it relates to? What does it do when it does that? Just give me your best effort. Okay, so the M what starts with a C, which is the X in the middle. Okay, so the F is turning the right, and this is a B. Okay, so the B adds doesn't have any number to be honest, but it just goes. It's like very very. It's kind of like tiny, but it's very very close to the M. So it really relates to those kind of relations to that kind of thing. So it really reminds me of karaoke, karaoke, just like things like that. It reminds me of um it reminds me if you're doing something in a like a Chinese game or like or just as simply uh it reminds me of when you're playing jacks, actually. Yeah, and when you're actually singing the karaoke, which means your song actually hears from this kind of thing, the movement of your song is actually made by it. So it can be like volume. So that could be more about it. Okay, so this one is very tiny, and this one is like kind of medium. This one is normal, and this one is actually very slow. Like not too slow, but just a little slow to that to get caught in structure to get awaited on. So yeah, that could be about those. If you guys have any questions about these harmonic motions, just let me know. All right, next page. All right, infrasound, infrasound, infrasound. Infrasound is sometimes referred to as low frequency sound, a sound that is lowered in frequency. Just like in frequency that I've done in 25, this will remind you of it. Just to let you know, guys. Ugh, darn, sorry. My apologies. Right. Sorry. All right. So like the infrasound is like just like the harmonic motion, but it's more like the infrasound when you're doing something like an app or something like that, when you're testing your voice or something like that. If you're actually new to YouTube, then you actually find it very completely different to yourself. So that's why has been completely on tap topic or something like that. That's how your voice can actually sound. That's how your voice can actually be tested for those kind of things. So yeah, if you want to try it out, you can. Okay, so the Infrasound Festival. So I don't know if there was an Infrasound Festival, but I don't know where it's at. Yeah, just like that. So, all right. So let's read this first page. So the infrasound, the extreme bass sound with the frequency lower than 220 Hz. There's a clown right there in the right, making it largely inaudible to humans, yet it comes to show up on various horror movies. Like screaming is like very high. So yeah. Okay, so why is tests have shown that listening to infrasound can cause extreme sorrow, dread, and shivers in humans, possibly because the sound is the same frequency as a tiger roar or a volcano, or maybe it's just because like it's also like powerful to enough to vibrate your potential organs, so that you can actually test your voice in different voices that you can actually do. Like you can use like voice app, all those things you can find in your phone. Let me know if you have one of those. All right, so the third picture represents too the frequency ranges of the sound. Like, so this lands on the almost the just like the 10. The blue line of the human hearing is actually the 16 Hz to 18 kHz. So this actually can remind you of those kind of things. So yeah, this blue one is actually the human hearing. So yeah. Okay, so the conventional power ultrasound is actually 20 kHz and to the 100 kHz. So it represents to the some of you guys might think it's like 10 4 squared to 10 5 squared. So even though it doesn't really say it on this graph, even though it doesn't really say, but it actually reminds you of it. So yeah, just bear with me on that. So all right, so the extended range for sonochemistry is actually 20 kHz to 2 million Hz. I did not realize that, but I just figured out now. So it's related to 10 5 squared to 10 6 squared. Okay, so let's try about the diagnostic ultrasound, which is a 5 million Hz and a 10 million Hz. Okay, so this is related to the 10 7 squared. So okay, so the diagnostic under ultrasound is like I'm gonna show you some answers later on the diagnostic ultrasound. I'm gonna show you some answers about. I'm gonna read some of those questions to remind you guys that the you guys can understand about the ultrasound way better. So you guys don't have to answer. You guys don't have to get stressed out or just keep up with your work. Just do all that. Just all those stuff. Or the infrasound is actually below the 20 Hz in a which is one of those curly worms that can translate to those kind of stuff, even though a big worm is actually kind of, even though it looks like a snake or a worm, that can be related to those kind of stuff. It's actually below the 20 Hz. Audible frequencies. Okay, so it's actually the 20 Hz to 20 kHz. So this is actually relates to those kind of the worms are like going really fast. It actually really seems to be really normal. So yeah, just like I told you about the harmonic motion is actually really familiar. You can actually find those really familiar. So yeah, like it actually is below 20 Hz. So this was the first one, and the second one is actually the normal. Just like in audible frequencies is how your voice can actually test. All right, what do you think the ultrasound is? All right, ultrasound is actually over 20 kHz, which is actually the third position. Just like in harmonic motion is like that can actually remind you of something. Just like the ultrasound when the curly worms are actually going really are going too fast, running away for their life. So just like all that stuff. Yeah, the ultrasound is like really, really fast, like really, really fast. In this third option, it's like even it's like over 20 kHz is actually the frequency that can be described or can be written about, which can be either described or written. Can be about you probably learned this for your teacher. Probably learned this for like probably probably in freshman. You guys should know this in like freshman year or something like that. Just like that. Okay, so that's all you need to know for this page. If you have any questions, just let me know. All right, kinetic energy. Kinetic energy. Just like I told you about the kinetic energy is about the movement. Like when things go really really far and things go really really alternative. It's actually about the part that I told you about. All right, so kinetic energy is of an object is the energy that it possesses to its motion. Just like when you're thinking about it, and when you think about it, you think about something really cool you want to do. All right, so the second photo that I'm going to show you is the Lamy stock photo. You see those two. You see those a lot metal. You see those kind of like gray balls. They're actually gray alamis that I can call. They're like in a tie with this line. You can actually see. Oh, excuse me, in a top. And so yeah, like the all four alamis are going like they're still four together, but the rest of them are actually catching up, and there's not enough lines to catch up with those because I don't think the line can actually fit in all those balls or all those alamis, whichever you call it, which all those alamis to actually fit in those kind of lines. So that's actually holding, even though it can try to, but some of them may fall off, or some of them may actually do a motion. All right, this fourth page is actually the kinetic energy. The potential energy is actually when you're actually trying to do something like archery, for example, that I tried in freshman year, which is a PE individual. Do you guys have any? Do you guys have PE individual? I know that I did. So yeah, it happens to my school. So yeah, most of you guys have like PE team. I just had PE team. I just had PE individual at first semester for freshmen and second semester for PE team. I honestly did okay in those times, but even though I wasn't dressed properly, even though but I wasn't really trying, but sometimes it's really important to dress in all times when you're trying, when you have more equipment to yourself, just like all those kind of things. All right, so potential is actually when a person is actually trying something new, like archery, for example, and it turns and when you're ready to do it. So the kinetic energy is actually the movement of the archery arrow. Is actually pointing to it's kind of similar to like the dart, kind of like when you're it's kind of like when you're doing the darts when you're pointing to the right spot that you're going to put in. All right, so the third picture represents to a man skateboarding in like a long down river. All right, so the kinetic energy, working energy motion, is actually a person looks so nervous, or a person looks so I don't know what he looks like there. What do you think he looks in his third picture? He probably feels like confused, or I don't know what he feels. Like he probably feels like scared, or he probably feels nervous. I'm gonna just say that he's nervous because he never tried those things before. He's like afraid that he's gonna fall, just like all those things. He's like skateboarding in the that's the movement of down there that you can actually give yourself some air to fall down and get hurt, which is not good. So, yeah, okay, so yeah, all right. Let me know if I'm going too fast, then I'll slow down for you. I'm trying not to talk as fast. We may get things done pretty quickly, but let me know if I'm going too fast because even though but I'm doing things more slowly than ever, so basically energy is the ability to do work. Just like the light bulb can actually tell you that. Alright, so let's start with this problem. The U is actually the arrow, and the M is actually the dot, this dot squared. So there's a person holding a gun and actually shooting something, trying out a gun, for example. It's like a pistol when you're actually shooting, when you're actually testing your shooting, that actually can tell you. This will tell you how much it costs, like how much it can afford. So the E equals mu squared divided by 2. This is the answer of a gun that has been taken, that has that movement of doing that in common. That's what a common actually looks like. So yeah. All right, that's enough for kinetic energy. All right, so let's move on with how many. All right, so how many? We have like 12 or 11. Okay. All right, so light energy. Light energy. All right, so light energy is the only form of the energy that we can actually see directly. So this is a light energy that has a lot of light, just like I did so many light videos that you can actually see. Is like I actually like to show my lights. My lights are showing in my room right now, which is that lamp, that tall lamp, so darn tall. Cannot. It's even taller. It's almost taller than my curtains, the curtain windows. Yeah, the curtain windows are like so taller. You can actually tell that by the difference between the curtain windows, by the curtains and the lamp, the huge lamp. Alright, so the like I said, the light energy is the only form of the energy that we can actually play or see directly. So this is a person holding a light bulb, and this is holding a light. Is that a light bulb or a light? I can't tell. Or a light bulb. I can say. Okay, so the representation is actually the light bulb. There's a lightning that usually happens often when we're having a storm. When there's that storm, the power goes out, and that's why I don't like about storms is when the power goes out. When I'm editing something, that's why that I see something directly. So, alright, so the fourth one actually represents the lightning that has two lights. The one has like the circular motions of that one, the one doesn't. So what does what do those need to be needed for? Why do those need to be needed for? Just give me your answers in the comments. Alright, so yeah, just all that in general. Alright, so that's enough for light energy. Let's just move on with the motion. Oh, 10 more, okay. Alright, so motion, right? Yeah. Alright, motion. Motion. Motion is a change in position of an object with respect to its surroundings in a given interval of time. Like, so you can see the time that is actually been taking a time, but you have to actually get things done. Like I'm doing, for example, is I have to watch my time closely to get my things done, get things done, and just get it over with. Just do more time in frequent time, so that can be more frequent to use your time wisely. So yeah, those are those red, green, and blue triangles. You can see those triangles separated above, separated in three, so you can actually see what is it like to be separated by those three triangles. So the movement by the train is actually motion. When you're actually doing slow motion or fast motion, is actually it actually fits together in whole. It actually all of it. So when you're actually doing more movements of the train moves really fast, and some cars move slower, which is I actually get tired of doing. I actually get tired of hearing it. So yeah, so this is a movement of those green balls that are that this block. You can see the that looks like an arrow that looks like the right up. Like this is what it represents. This is what motion actually looks like when when it actually stops. The green balls usually drop, but they don't do that because it actually has been taken in that picture. But what do you think it's doing, guys? It goes for all of you. What do you think it does? Just give me your comments. All right, enough for motion. Let's talk about the Newton's third law. Newton's third law. So back in a long time ago, back in third grade, I actually learned about the Newton's third law. I actually learned about the Newton's laws. They are actually uh, they're actually equal and opposite reaction statement means that in every interaction, it can and it can and it can actually be the movement that has been represented when I just had to end those parts. Yeah, like I learned it again back in Mr. Murphy's in freshman year, and Newton's third law is actually interesting to me. So that's why I keep moving things all the time. So yeah, that's why I keep doing things like that. I usually do accidents. So yeah, that's what balance is actually for. That's what balance does is actually more accidents when you accidentally did something to your computer or your phone. Can be any of those stuff. Or if you forgot something like a book or something like that, that's actually balancing when you're actually trying to do a skateboard. When you forgot something, it's actually a different level. It's not just a balance enforcement. It's actually different enforcement. So yeah. All right, Newton's third law. Repeat. Newton's third law. Newton's third law is an equal and opposite reaction statement means that in every interaction. Like so, for example, the fourth picture that the jar of glass. All right, so I forgot to tell you about the gravity. I'm sorry. Okay, so the gravity is something that drops really, really hard. When something drops, that's actually gravity. So, I learned about the gravity since like in third grade, obviously. I actually noticed around like age of 4, I noticed something that can drop very easily. I know that these can actually break pretty easily, so that can be pretty much about it, about the movement that the or glass or foam that can actually break if if you had the screw that is actually made out of something. What do you think it made out of this? When a glass breaks, it really breaks, obviously. And so there's a jar that is actually in down or an up. The jar is actually standing in the purple. So yeah, the Newsford law in action reaction. So I'm gonna represent to those. Okay, so in the middle picture that is actually, okay, so the tractor, and the person in the middle, or in the elephant in the right. Repeat: the tractor in the left, person in the middle, in the right is the elephant. You can see the man is actually squished by those tractors in the elephant. Not the elephant, because the elephant is actually tied up. I don't know what that man is actually doing, but like, what do you think he's doing? What do you think they are doing? I can actually tell is that actually the equal and opposite reaction statement means that is every interaction. So that actually means, if you're sitting with people, then you actually sit with the opposite reaction that's actually adjacent. That can be actually represented to those kind of things. So, yeah, or so yeah, that's all about it. So yeah, all right. So the first picture is actually the ball is actually down there, and the line's actually the arrow is actually pointed up, and the ball is um actually right there. So yeah. And so the every action has an equal and opposite reaction. So this actually represents to that picture, that first picture right there. So is where my mouse was. So yeah, like there's a line that there's a lot of blue lines in the and the balls and the ball is in a circle or a ball that can be actually blue, that is actually stuck in the line that is actually in the left. So yeah. All right, so the fifth picture, that the last picture that has been replaced, is actually the lift of the baseball. I actually seen this before. It's actually given Research Center. And so Fiore is actually this black ball that has been in the middle, and the lines are actually curled a little bit, curled up. But some of them are not. But these two are actually just normal lines. But some lines are actually legally so. Yeah. At least if the spin is actually 5, the velocity is actually v, density equals p, and radius actually b. At least if the preference is actually the baseball that has that actual movement, that actually has that lift. What do you think those numbers are? What do you think the answer is baseball? What do you think the answer for this baseball? What do you think that answer is? What do you think it is? Theoretical lift equals 4 divided by 3, in parentheses by 4 pi 2 squared b 3 squared sp and v, in the parentheses. So the reference lift is actually measured on baseball. Lift confident equals reference equals CL equals 0.15 theoretical. Right, so the lift equals L equals CL x 4 divided by 5. I don't know if it says 1 or an L or an I. Actually, let me start over. Lift equals L equals CL or C or C or C1. Sorry. Actually, C1x. Right, so 4 divided by 5 in parentheses by 4 pi 2 squared b 3 squared is S, P, and V in parentheses. Like so the second picture is actually representing to the Newton's third law is actually I push on the door, third law, door pushes back on me. So that actually when the person actually gives you some if a person wants to talk to you, like your family members, for example, if they want to talk to you something important, if you're like actually mad at something, when your mom is actually pushing your door back and when you're not letting your mom in, that's actual the movement. That's actual the Newton's third law. So yeah. Third law in pairs. Third law pairs actually I pull on the door pulls back on me. I pull on the door and the door pulls back on me. This actually is a representative to those people that are actually doing it. So my force on the door is actually action force equals the door's force on me equals reaction force. So that could be that can actually represent in the Newton's third law or in other Newton's laws. So many Newton's laws that can actually be described in your. You probably learned this for like in third grade, definitely. I notice when I get angry sometimes I usually push my door a little bit harder, and my mom tries to get in, and she tries politely to politely to push, and I pull really hard. And I actually push, and my mom pushes, and I pull, and my mom pulls sometimes. Yeah, when you're not sharing the door, what would happen to that door? The door would just keep on moving, or something like that. All right. See you guys on part 27, and if you guys have any questions, just let me know.